because the Ahmad I put him on second place because he told us that he has some, how to say, that must to finish earlier. Is it Ahmed here? No. The third person is now second person, and we will continue, dear Marcel, because Dorian Edelku is on 5 page, and continue with Streamlight and Basic Android, and you will see another parts. This is Kamal Sehairi. Is it okay, Sehairi?
Hello, Teomir.
Yes, thank you.
Audience.
I see I see you online here after chatting on the internet, and Kamal has a paper, embedded GPU acceleration of object detectors using NVIDIA CUDA. Please, Kamal, start your presentation, and I am very happy that you are with us.
Thank you. My pleasure to be with you, dear my
Be
friend.
careful, just open it. Do you have 1 or 2 screen?
Yeah, I will share my screen, of course.
Okay, share it. Just okay. I haven't lacked the access to share my screen. Can you give me the access to? You all participants, okay? Yes.
I did.
Yes, okay.
Thank you. Is my presentation open for you?
Yes.
Okay.
We
Chairman, honorable audience, hello. Let me first of all express my deep appreciation and gratitude to all who gave me this opportunity to present my work entitled Embedded GPU Acceleration of Object Detectors using NVIDIA CUDA. For this, we have adopted this plan, starting by an introduction that will talk about accelerated computing. Then we will present our development tools, the traditional object methods used in this study, and we will show our results, implementation results. We finish with conclusion. First, we will try to, in this work, we will try to answer this question: can we implement object detectors in real time on sophisticated embedded systems? Can we take advantage of embedded GPU on some sophisticated embedded systems to accelerate computing? How much speed up does the object detector embedded GPU implementation achieve compared to CPU implementation? And finally, is the accuracy affected by this GPU implementation? Of course, object detection is a crucial high-level computer vision task in many applications, such as image understanding, process automation, surveillance, medical imaging, retail management, etc. It involves the use of machine learning techniques that incorporate data collection, data labeling, training, validating, and finally inference running. To ensure proper function of these smart computer vision systems, the system must operate in real time. Real time in this case is having the same image stream between the video source input and the monitor output, which means that the processing time should not exceed the time of image acquisition, which is often 25 frames per second or equivalent of 40 milliseconds. The massive amount of data in videos and the higher complexity of machine learning methods for object detection cause computation load and often exceeds the processing capacity of convolutional machines. What we mean by convolutional machines, any CPU, central processing units on our laptops or desktop PC. For that, we need special accelerators such as digital signal processors, parallel processors, graphics processing units, ASICs, visual processing units, tensor processing units, neural processing units, or field programmable gate arrays. In this study, we will use embedded GPU on embedded systems. So software optimization can also be utilized along with the hardware approach to reduce computation complexity. This includes algorithm optimizations, which involves the exploitation of image symmetry or image size reduction, code optimization, which uses special libraries optimized for specific hardware platforms, and finally, code vectorization or reduced precision techniques. On embedded systems, we have to choose the best accelerator with the best code optimization, parallelization, and precision reduction techniques. In our work, we used the Jetson Nano board released by NVIDIA in 2019. The board comprises system on module presented here. And this system on module is mounted on carrier board, mounted here. The system on module comes with Tegra X1 system on chip, which has quad-core ARM Cortex-A57 operating at clock cycles of 1.43 gigahertz and has 128 embedded GPU cores with Maxwell architecture. The SOM also has 4 GB of DDR4 and a video encoder-decoder with mini resolution. The carrier board has many input-output ports as presented here in this figure. The Nano runs Ubuntu Linux for Tegra, operating system, and it's based on Ubuntu 18.04. It comes as a bundle called Jetpack SDK that comprises the operating systems and different development tools and libraries, such as CUDA toolkit, which is a parallel programming development environment for C and C++ developers building GPU accelerating applications. It includes math libraries, compiler, debugger, and optimizer, and a CUDA, a QDNN library that provides an optimized GPU implementation of different DNN, deep neural network layers. And finally, TensorRT, which runtime specialized for running deep learning neural networks and optimize. The Linux for Tegra operating system comes also with pre-installed drivers and libraries. Among these libraries, we find the OpenCV, which is a pure version of the Open Computer Vision library with no optimization for Tegra and no CUDA support. That means that it has no CUDA accelerated computer vision module and pre-installed with the board. However, to take advantage of from GPU cores, we must build OpenCV from source with CUDA support to ensure parallel computing and take advantage from the accelerated computer vision algorithms. The installation process is hard and takes about 6 to 9 hours. For full instruction, please consult my report on ResearchGate. It has step-by-step how to install OpenCV with CUDA support on Jetson Nano board. First method that we have implemented is the hard cascade classifier presented by Viola and Jones in their paper Rapid Object Detection using Boosted Cascade of Simple Futures. The algorithm executes in several steps. First step is pre-processing. It involves color conversion and histogram equalization. The second step is applying a sliding window to extract hard-like futures. To accelerate computing of hard-like futures, the authors used the integral image which is a representation where each pixel values is the cumulative sum of all pixels above and to the left of that pixel. And finally, we construct our weak classifier and we evaluate. We have to initialize the weights, training weak classifier based on the hard classifier and threshold, compute the error to evaluate this weak classifier, and select the best weak classifier with minimum error. Then update the weights to give more importance to the misclassified samples. From these weak classifiers, we have to form a strong classifier by combining them. Finally, we apply no maximum suppression to refine detections. Sorry. The same for the histogram-oriented gradient methods, which presented by Dalal and other authors in their paper, Histograms of Oriented Gradients for Human Detection. The algorithm executed in several steps. Also, the first step is pre-processing, color conversion, and image normalization. In image normalization, we can use gamma correction, mean subtraction, gradient normalization with L1, L2 norms. Then we have to compute gradients, magnitude, and direction using one of edge methods such as Sobel, Prewitt, or Canny. Then we compute, divide the image into small measure regions called cells. And for each cell, create a histogram of gradient directions, typically 9 beams covering 0 to 180 degrees for the direction of each pixel. Then we have to concatenate the normalized histograms or blocks to form single future vector that represents the entire image. And finally, slide detection window over the image at multiple scale and position. At each position and scale, extract the Hawk features for window region, use training classifier, separate vector machines, for example, and to determine whether the window contains the object of interest. And same as the hard cascade classifier, we have to apply non-maximum separation to eliminate redundant bounding box. For the implementation, hardware implementation, we have divided our implementation. For image acquisition and encoding and color conversion, we have executed this on the host side, which is the CPU, the ARM CPU processors. And we have taken the advantage of using Linux for Tegra to encode and decode our video images. And this ensured using video for Linux media controller sensor driver API. After that, we have to upload the converted image onto gray image to the GPU memory. Then the hard cascade classifier steps, all the hard cascade are executed on the GPU side. Finally, we have to download the results, which contains the bounding box coordinates on the host side to display it using the same video for Linux multimedia API. The same for the Hog method, acquisition and color conversion is done on the CPU side, while the image processing and all Hog method steps and non-maximum separation techniques are done on the GPU. The result is downloaded to be shown using the video for Linux API on display. For the parameters, the scale factor, which specifies how much the image size is reduced at each scale, was set to 1.1. The minimum neighbors parameters, which limits how many neighbors each candidate rectangle should retain, was set to 1. And the minimum possible object size was chosen as 30 by 30. And these parameters was selected for the same CPU implementation and GPU implementation. For the Hog method, the scale factor was set to 1.02, and the window size was set to 64 by 128. The block size to 60 by 60. The blocks tried to 8 by 8, and the cell size to 8 by 8. The number of beams was set to 9. And the threshold for the distance between features and the SVM classifying plane was set to 0. The reason we have chosen these parameters, That's because the CUDA implementation on OpenCV 4.9.0, the latest version, has just these parameters, accepted parameters. Evaluation and performance comparison were done on the PETS 2009 dataset using different resolutions. And the Raspberry Pi 4 implementation is added for comparison purposes. The Raspberry Pi has Broadcom system on chip, BCM 2711 with quad-core Cortex A72 ARM v8, and has 8 GB of DDR4. This figure shows the result of implementation in frame per second for different configuration and methods. We have the Raspberry Pi CPU HAR cascade classifier, the Jetson Nano implemented on the CPU side of the HAR cascade classifier implemented on the CPU side of the Jetson Nano. The HAR cascade classifier implemented on the GPU side of the Jetson Nano, and the HOG histogram gradient implemented on the CPU on the Raspberry Pi. The same method implemented on Jetson Nano CPU, and the same method histogram integrated with group rectangles, which eliminate redundant bounding box implemented on the GPU side. And another method with non-maximum separation is implemented also for the GPU side. We see that the fastest method is the HAR cascade classifier on the Jetson Nano, because the HAR is less computation has less computation load compared to the histogram of gradients, of course. And all the systems can be run on real time, as we see. For VGA resolution, we see that here that the GPU side, the implementation of HAR cascade on GPU side, it has the fastest implementation compared to the others. And we start to see that the GPU implementation of HOG, histogram coordinates, is fastest than the CPU implementation. For high resolution, 1028 by 960. Also, we have also the HOG, the HAR cascade classifier on GPU is the fastest than the HAR on the CPU. After that, the histogram oriented gradient on the GPU side. And for this resolution, none of this implementation can run on real time. This figure shows the results of detection algorithm applied on this sequence from the PETS 2009 datasets. This table shows the overall results across all implementation, precision recount, and F1 score was used as metrics. We see that the histogram of oriented gradient GPU NMS, known with no maximum separation, has the higher resolution, the higher sensitivity, and therefore a higher F1 score compared to the other methods. Besides, we have used the same parameters for same methods. As conclusion, we successfully developed and implemented traditional machine learning object detectors on high-end embedded systems. We use the most important characteristics of GPU, the parallelism in data and computing, by employing OpenCV CUDA optimized functions. And the optimized function of OpenCV CUDA shows significant improvement compared to the CPU implementation in computational time and precision. And as future work, we intend to implement other object detection methods, traditional and deep learning methods, exploit different DNN, deep neural network optimizers, and runtimes. For example, we can use the TensorRT from NVIDIA, and we can use the OpenVINO from Intel Corporation. We can use NPU, neural processing unit from the Huawei Ascend technology. Also, use of different hardware accelerators such as FPGA, Xilinx Kria FPGA, or the tensor processing tensor board from Google, or other hardware like neural computing stick from the Intel. This is my presentation, and thank you for your attention. And any questions, please.